in the previous module, I talked about the relationship for Lz and Ly, that's z component of the angular momentum and the total orbital angular momentum. And this we got from by using the simple equations of Px, Py and Pz operators, linear momentum operators, which I said you, it's minus IH cross d by dx minus IH cross d by dy minus IH cross d by dz. Okay, so using these we got the equation in spheric in Cartesian coordinates, and then I said you we can it can be converted into uh, spherical polar coordinates in terms of theta and phi, and I gave you the relationship in for these Lz and L square operator. Now what we can do is that we can operate with this operator on a function and we can get eigenvalues. And one of these operations I talked about when I talked about the derivations of phi equations in rigid rotor. And if you remember, the phi equations when I derived the eigenfunctions which we got was, if you have an operator Lz and the eigenfunction is 1 by root 2 pi exponential minus Im phi. This is the eigenfunction which you get by solving phi equations in rigid rotor or in hydrogen atom. In both the cases the same thing. Okay, so for hydrogen atom or for rigid rotor, the three equations we got: phi equations, theta equations and R equations, and I said the simplest one was phi equation, so we did first phi equations in rigid rotor. Okay, and the phi equation solution and after normalization we got 1 by root 2 pi as the normalization constant, and this is the solution exponential plus minus Im phi. Okay, you can write plus minus Im phi is the solution. Okay, so if this is your eigenfunction and if this is your operator, then we operated with Lz operator on this phi m function, and what did we get? What we get is exponential minus IH cross del by del phi is the Lz operator. Okay, I in the previous module I derived this one, and I said you that in contrast to Lx and Ly, Lz operator is very similar to the linear momentum operator. So it's the minus IH cross del by del phi, and same way for if you have to write the Px operator in the linear momentum operator, then you write minus IH cross del by del x. Okay, so it's very similar. Lz operator you cannot forget because linear momentum operator you are doing from the very beginning. Okay, so minus IH cross del by del phi, and then the eigenfunction is 1 by root 2 pi exponential minus Im phi. What will be the value? The value will be minus IH cross will be here, 1 by root 2 pi the constant, so you will bring it this side, and then if you differentiate, what you get? Im exponential minus exponential Im phi. Okay, plus minus Im phi both, but anyway I have written Im phi, so it will do. And then what you write? So it's what? Mh cross. This I and this I you multiply, it will be I square, and I square is minus 1, so minus and minus will go. You will have 1 plus, and this m will remain and h cross will be there. So you will have mh cross 1 by root 2 pi exponential minus Im phi. So if this is your result of operation of Lz operator, then what does it tells you? It tells you it's an eigenvalue equation, because you are getting phi m on this side and phi m on this side with a constant mh cross. So the eigenvalue is mh cross, and this we did earlier also when we were talking about phi importance of phi functions. Okay, so this is the eigenvalue. What about, and then we say that Lz phi m, what you get is mh phi m. Obviously, where this m earlier we did it was 0, plus minus 1, plus minus 2, plus minus 3, and so on. Okay, I said you this m is the magnetic quantum number which you get from the solution of phi equations. Okay, and the magnetic quantum number value you know it is 0, plus minus 1, plus minus 2, plus minus 3, but it has the limitations. Upper limit is there. We will talk about that in the later on. Okay, so it will not keep on increasing up to infinity. It has upper limit that the total number of values will be equal to 12 plus 1 values you will obtain. That we will see. Okay, so Lz you get this one, and the eigenvalue of Lz is mh cross. Now operator L square is what? Minus h cross square 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square. And if you remember, when we did the theta equations, we got a solution for the eigenfunction spherical harmonics y10 as root 3 by 4 pi cos theta. Okay. So if this is your eigenfunction and this is your operator, then you operate with this operator on this eigenfunction and you try to find out L square y10. L square is the operator, L square y10. So this should give you a constant multiplied by y10, then only it will be an eigenfunction. That's the basic definition of eigenvalue equation, that you should get a constant multiplied with the same function. So I'm repeating it time and again because you should not forget these basics. Okay. So if you apply this, what will happen? Minus h cross square 1 by sin theta del by del theta sin theta del by del theta plus 1 by sin square theta del square by del phi square is operated. This is your operator and this is your eigenfunction root 3 4 pi cos theta. You have a function cos theta and in this part you are differentiating with respect to phi. Okay. So this second part will go. Okay. This differential will go, and what you will have root 3 by 4 pi the constant, so bring it outside. Now you have 1 by sin theta, this 1 by sin theta, del by del theta, sin theta, and del by del theta of cos theta. This you write. Okay. And what will be the result? Del by del theta of cos theta will be sin theta, and this sin theta multiplied by sin theta will be sin square theta. So finally what you will have? 1 by sin theta, again del by del theta of sin square theta. Okay. And this sin square theta will be what? Sin square theta will be 2 sin theta cos theta. So if you put this value, what do you get? 2 sin theta cos theta divided by sin theta, and sin theta will go, and you will have root 3 by 4 pi, 2 will come outside, 2h cross square cos theta. Okay. And again what you get, this is actually y10, so it's a y10. So operating with an operator L square on a spherical harmonics y10 gives you a constant value of 2h cross square multiplied by y10 on a particular spherical harmonics. We applied and we operated with L square operator and we got this equation. So this is a constant. Okay. In general, this equation could, sorry, it's already there, written there, so I am omitting these things. Okay. These notations is not required because everything is written. Okay. So what you have is L square y10 is 2h cross square y10. If you write a general formula for this kind of operation on ylm, it was y10. It could have any combination, 1 plus minus 1, 1 plus 1, 1 minus 1, 2, 2 plus 2, and something like that. Then generally what we got is L into L plus 1. Okay. Now you see your spherical harmonics y10, and what does it mean? For this, L is equal to 1 and M is equal to 0. So if this is the general relationship, then L into L plus 1 will be 1 plus 1, 2 multiplied by 1 is equal to 2. So that 2 you got here. Okay. So the general relationship for application of L square operator on a spherical harmonics is that it gives L into L plus 1 h cross square ylm. Okay. So Lz operator gives you, Lz operator when operated on phi m gives m h cross phi m value, and L square operator when operated on ylm gives L into L plus 1 h cross square ylm. Okay. So these are the eigenvalues of Lz operator and L square operator. Now, what is the physical interpretation of the eigenvalues of Lz and L square? We operated and we got the eigenvalues. Now, how do we physically interpret this? These are the two relationship which we did in the previous Now you see the total angular momentum L is given as root under L into L plus 1 h cross, where small l is angular momentum quantum number. That's azimuthal quantum number you say. Okay. This azimuthal quantum number has a value 0, half, 1, 3 by 2 and so on. Okay. And this Lz phi m is equal to m h cross it gives, and this m is called magnetic quantum number. Now you see both all these are you were already aware qualitatively. You were knowing that you have a azimuthal quantum number, you have a magnetic quantum number. Azimuthal quantum number is also called angular momentum quantum number. So all this fact was known to you. Now m goes from minus L to plus L in n integer step. Okay. So for a given value of L, there are 2L plus 1 value of m. Again, it's a fact which you know. I am saying you, we will prove it that why it is so that 2L plus 1 values of m. It's a fact which you know, so I have written it. Okay. But we will see why it is so, 2L plus 1 values. The vector L is oriented in a space in such a way that its z component Lz has 2L plus 1 values. This is very important. Because if both this L, a small l, and m is not independent, they are related to each other. So we say that the vector L is oriented, the vector capital L, means total orbital angular momentum, is oriented in a space in such a way that its z component of the vector L has 2L plus 1 values of Lz, because 2L plus 1 values of m is possible. So 2L plus 1 values of Lz is possible. Okay. Because I have written here 2L plus 1 values of m is possible. So this m will have 2L plus 1 values. It means Lz will have 2L plus 1 values. Okay. And values from what? Minus LH, minus L plus 1 H cross up to 0, and then again it's like this one, minus 2, minus 1, 0, plus 1, plus 2, and again you write H cross, H cross, H cross, H cross, and H cross. And this is what you write in magnetic quantum number, from minus 2, minus 1, 0, plus 1, plus 2. So this many values of Lz you will get for a particular L. Okay, because Lz is equal to mh cross and L is equal to root under L into L plus 1 h cross, and the value of the two m and L is restricted by 2L plus 1 values. The value of m is restricted by 2L plus 1 value. So what does it mean? It means that if you have a condition like this one, Lz, this is the Lz, z component. Z component is vertically in this direction. This z component. Okay. Then this is Ly component. Now you have this Lz component in this direction. All these red lines are the components of angular momentum. Okay. All these red lines. So how many lines you have? 1, 2, 3, 4 and 5 for a value of 2. So plus 2, plus 1, 0, minus 1 and minus 2. This is x component, Lx and Ly value. Lz is along this direction, and for a L is equal to 2, you will have 2L plus 1 values of Lz and 2L plus 1 values of Lz is, it's not written here, you can calculate the magnitude also. So for each of these, so these are component, first, second, third, fourth and fifth component of z momentum. Now you see that this particular diagram shows you the direction of motion and Lz component also. So L and Lz. L is will be this is the direction of motion, and this Lz will have different magnitude. So this magnitude will be plotted like a curve like this one when Lz is goes, and that's very important motion, that's called precessional motion, and it has very much relevance in spin spectroscopy that certainly I will not be doing in this module, but sometime if you go and you find the precessional motion, you revisit this angular momentum module and you will see how do we get the LZ component motions. Okay, so this angular momentum values, so this is the physical significance of the value which you obtain from operation of LZ and L square. On the LZ you operate on phi functions and L square you operate on a spherical harmonics function. Okay, and this also leads to a space quantization. This is what's called space quantization. So precessing LZ component of angular momentum, since Lx and Ly is unknown. Okay, we don't have the Lx Ly value, but Lx and since Lx Ly is unknown, so it will precess and it will show a motion like this one. It will be a motion like this one, and this is called precessional motion. Okay, this is called precessional motion.